yourself. GSI Pushpa Bhavan, please mute yourself. আমার স্পিকার অফ আছে GSI Pushpa Bhavan, please mute yourself. এখানে একটা অন আছে বোধহয়
Warm welcome to Dr. Saibal Gupta, Professor IIT Kharagpur. Today, right now at this moment, we are going to have a technical deliberation on lightning using heat from with an Indian shield by Professor Saibal Gupta. So we are all eagerly waiting for that, and I welcome him once again to and start the deliberations. Thank you.
Respected DGGSI, and we, on behalf of GSI, we cordially welcome Professor Gupta today for giving us a very informative lecture on lightning homes using heat from within geothermal reservoirs in the Indian Shield. Let me just give a small introductions, though I cannot tell a lot of things about him. It's a small introductions only, but you can easily identify the era of the field where he is operating and he is working. Professor Gupta graduated with BSc Geology honors from Presidency College, Calcutta in 1987, and he did his MSc Geology from University of Calcutta in 89, and he was the Nehru Cambridge Scholar. He did his PhD from University of Cambridge in 1995, and his fundamental expertise lies in integrating structural geology with metamorphic petrology, which he uses to reconstruct geodynamic processes and tectonics. He has also initiated planetary geology research at IIT Kharagpur and worked on problems on lunar and Martian geology in collaboration with ISRO. To date, he has published more than 78 papers in the peer-reviewed international and national journals encompassing all these domains. His contributions have earned him the fellowship of the West Bengal Academy of Science and Technology in 2014, the INSA Teacher Award in 2019, the National Geoscience Award in Basic Geosciences in 2022. He was also the first Professor P.K. Bhattacharya Chair Professor of IIT Kharagpur from 2022 to 2025. Currently, he is the Dean Faculty of Geosciences in IIT Kharagpur. So I invite Professor Gupta to start his talk.
Very good afternoon to one and all. I hope I can be heard. Let me just begin by first of all saying how honored I am to be invited to give a lecture on the occasion of the 175th year anniversary webinar series of the Geological Survey of India, one of the most hallowed institutions of India in the past as well as today and in future. It is my job as a geologist today to actually hold up before you how important this domain of geology is and the extent to which the Geological Survey of India can actually contribute even further to whatever our country aspires to be within the next century or so. To talk about myself, I'm Saibal Gupta or Gupta as you, whatever you prefer. I have been a professor at the Department of Geology and Geophysics at the Indian Institute of Technology in Kharagpur for over 30 years. I've been teaching and doing research there on varied domains. Whatever I'm talking about today is an outcome of my fundamental expertise, which is in structural and metamorphic geology. Whatever I'm talking about, whether I do planetary geology, whether I do geothermal energy, or whether I talk about critical minerals, everything is rooted in what I fundamentally started off with, structural geology, metamorphic petrology. And using this is something that came as an outcome of the work that I did. And what I decided to talk about is something that is very important in today's world, especially in the context of energy today. I was thinking of energy sources inside the Indian Shield, something that we need, desperately need as a developing country, and that is to get this energy from inside the earth, geothermal reservoirs. We live in the Indian Shield, so I just thought, why not actually think whether there is any possibility in a country such as ours for using the heat that we get from geothermal reservoirs to actually light up our homes. Let's see how much we can actually do based on it. So all this begins with a number of players involved.
Why is not presentation there? Then how will they see? How will they see?
क्लास जो चल रहा है.
So it's visible, presentation is visible here.
Right, sorry about that actually, I'll just continue with here. So all the work that I've actually done has been in collaboration with a number of people. Oshmita Moitro, who was my PhD student and was a Royal Society Newton International Fellow at the University of Southampton. Anupal Jyoti Datta, who has been involved in the last phase of this work. He's a research scholar, just about to submit his PhD from the Center of Petroleum Engineering at IIT Kharagpur. Anand Singh, who is now an assistant professor, a geophysicist at IIT Bombay. Shubham Bose, my own PhD student, who is now an assistant professor at IIP in Visakhapatnam. Dr. Tirumalesh Kesari, who is a scientist in the isotopic hydrology division of Park Mumbai. Professor S.P. Sharma, long-term colleague of mine of geophysics at IIT Kharagpur, and Dr. Sandeep Kulkarni, an associate professor who is the supervisor of Anupal, who's been actively involved in this collaboration that we've set up. The thing that I would ask you to note is that each and every one of them are Indians. This work has been done completely and utterly in India, and the collaborations are largely well within IIT Kharagpur. The only person outside here involved is Dr. Tirumalesh Kesari, and this was part of a project that we were once involved in. Now, all this actually begins, the story begins with the search for energy. And when we need energy, we know that the primary sources that we have today in today's world is coal and petroleum. Our country is dependent on it, but we know that we need to curtail the use of coal and petroleum because of their greenhouse effect. Of course, we can use nuclear energy. This is clean energy, but this requires a lot of investment. It requires a lot of safeguards. We can use solar energy, we can use wind energy. These are clean energies, but their utilization requires technology that involves the involvement of a lot of critical raw materials, not all of which is easily available from our country. Finally, of course, we can also talk about geothermal energy. We know that this is a major source in many places, but this is a major source in specific geological settings. Would this be applicable to India? This is what I would like to actually discuss today. Now, if you look around the world, geothermal energy usage has been quite prominent and it's becoming increasingly important. Microsoft G42, the Saudi Arabia consortium who is actually dealing with these things, have actually decided to build a geothermal powered data center in Kenya. There is a cooling load data center also built in Colorado. Google has recently invested $462 million in Utah again for cooling their servers. You also have a number of other sources in Taiwan. Google has also made, I think, in Taiwan, which is a geothermal power center, again, for cooling the data centers. So this is something that is becoming increasingly important. And what you see, the figure that you see on this particular part here is this facility that has been developed in Kenya. What you see on the left is a schematic representation of the way in which geothermal energy extraction is envisaged. So if we look at the places where geothermal energy has been and is a major source of power, most of these are either volcanic regions or regions that are tectonically active. So what are these regions? Iceland, for example, but Iceland is located on the mid-Atlantic ridge. New Zealand is located on the plate boundary between the Pacific and Australian plates. It's a subduction zone as well as a transform fault, right? All of these are on plate boundaries that are thermally perturbed zones. Kenya itself is located on the East African Rift Valley. It's a place where the African continent is currently being pulled apart. Utah, initially it appears that it would be an innocent place completely free of any tectonic association. However, Utah, the location from which this geothermal energy is being extracted, lies at the junction between the Colorado Plateau and the Basin and Range Province. The Basin and Range Province is a province that is being actively extended in the present day. So all of these areas have some kind of tectonic association. So these are all tectonically active. Now, in spite of this, because of the pressure from different sources, we know that we have to increase the sources that we have for clean energy. So wind and solar are fine, but what about geothermal energy? India's importance to this, you can see the date, the 15th of September in 2025. It really is a reaction really to the energy crisis that is enveloping the world, particularly our country, which is such a rapidly growing economy. And to grow our economy even faster, to cater to all our needs, we need more and more energy. So the Ministry of the New and Renewable Energy, MNRE, this has actually sanctioned the exploration both of deep and shallow geothermal resources. Now, it's all right to sanction, but where do we begin to look for these geothermal resources? We need to do the geology for it. The Geological Survey of India, for example, is the major organization in the country that has to lead this effort. But where would they begin looking? It's not as if you can just extract it from anywhere. But the most obvious sites that we know of on Earth are places where we can see hot stuff coming out. Apart from volcanic regions, these are regions where we can see hot springs, hot water coming out from inside the Earth. Now, when we look at hot springs around the world, you can broadly classify them into two types: volcanic hot springs and non-volcanic hot springs. Now, the one on the left, the part that you see here, the figure that you see here, these are volcanic hot springs, which means that these are in active volcanic regions where there is a magma chamber somewhere below the crust from which heat can be extracted because it's close to the surface, which has enhanced the geothermal gradient. So the heat flow, which is the conductivity into the geothermal gradient, means that the heat flow there is higher. It's extractable heat. But of course, we also have some places where you have non-volcanic hot springs where there is no obvious association with any kind of volcanism. There is no obvious association with any kind of tectonism. Now, if we look at our country has very few volcanically active regions, and only the very northern boundaries of continental India are tectonically active. In fact, if we look at the bulk of our country, we are fortunately or unfortunately non-volcanic. And indeed, again, fortunately or unfortunately, we are also largely tectonically stable. Much of it. We do have earthquakes, we do have seismically prone regions, but broadly, compared to, say, Japan, say, New Zealand, say, Iceland, we live on stable continental crust. So, in that case then, why do non-volcanic hot springs exist? It's normally considered that these are related to deep-seated fractures inside the crust, and water from the surface percolates to depth and gets hot. Why does it get hot? Because the Earth has a natural geothermal gradient. So as water goes down, because the rocks are hotter, the water gets hotter. And therefore, that is the water that comes up as hot springs. This is the broad, we can even say, a very elementary idea that we have of the existence of hot springs in regions that are not volcanically or tectonically active. Now, why does the Earth have a geothermal gradient at all, and what sort of form does it have? We have primordial heat, and of course we have radiogenic heat production inside the Earth. Both of these together combine to make the interior of the Earth hotter than what we see at the surface. Now, if we think of a 1D heat conduction equation to reconstruct geotherm we have under normal equilibrium conditions, so the equations I have here are for what are called the equilibrium geotherm. So this is the equation for stable continental crust, which is not being perturbed with time. It's steady state conditions. So the temperature at any depth below the surface, that is at depth Z, let us say, it can be calculated from this equation, where A is the heat production inside the crust, broadly the radiogenic heat production, K is the thermal conductivity of the rocks, Q0 is the surface heat production, right? And the dou T by dou Z that you see here is really the geothermal gradient that you calculate at any specific depth here. The thing that is important when you look at these equations, QZ0 by K, for example, for the geothermal gradient, this is a constant. The surface geothermal gradient, thermal conductivity. But you see here that the negative part of the equation has depth as a function. So as you go deeper into the Earth, it means that the geothermal gradient is going to decrease. So the surface geothermal gradient, which in most shield areas is around 25 degrees centigrade per kilometer, is not going to be 25 degrees centigrade per kilometer as you go deeper down. It's going to get lower. So the geothermal gradient at the base of the crust might be as low as 10 degrees centigrade per kilometer or so. So therefore, the geothermal gradient lowers as you go deeper down into the Earth, although the temperatures will continue to increase. So therefore, this is the broad idea we have. We have heat inside the Earth, but the heat that is indicated from the surface geothermal gradient does not necessarily translate linearly with depth. Now, this brings us to the problem associated with these non-volcanic hot springs. If we have deep-seated fractures present that guide the water down, are these fractures the only way in which we can get non-volcanic hot springs? If we get this, we are seeing water coming out of these non-volcanic hot springs. What is the source of this water? Is it all water that is originating at the surface? If it is water that is originating at the surface, how deep can such water percolate? Especially if the areas are non-volcanic, if they are stable regions of the continental crust. If they do percolate to depth, can we constrain the depths from which these waters are derived? So we're seeing hot water at the surface. Do we know how deep it's coming from? And then finally, of course, the question that we would like to answer, can the heat that we're deriving from these hot springs, can these be used as energy sources? Now, I am going to talk about specific cases that I've worked in, but this is by no means case specific. I would like to think of what the work that we've done as being generic in nature, that if you can apply this principle, it's possible that we might be able to make use of an energy which is essentially not just renewable, but unending, at least in our lifespans. So we're going to talk about a particular area where we've worked. We talk about a few hot springs that are located within the Precambrian continental shield region of peninsular India. And this is a region called the Eastern Ghats belt, a belt where I've actually worked for much of my life here. Now, what is the Eastern Ghats belt? Now, if you look at this map of India, we have of peninsular India, you have a number of stable cratons. At the eastern margin of the craton, you have what is called the Eastern Ghats belt. It's popularly known as a mobile belt of Proterozoic age, imagined by most of us to be a mountain chain that originated due to some kind of continental collision in the Proterozoic. Now, this is a map which has actually done brilliantly by the Geological Survey of India. So it's the famous map of Ramakrishnan, Jekananda, and Augustine, published in 1998. So which has a broad geological outline of the lithologies that you can see, the condolites, the charnokites, the bigmatitic quartz feldspathic gneisses, and the alkaline complexes, all within the Eastern Ghats belt. Now, this is the lithological map. Later on, as more and more geochronological information began accumulating, we have now decided that the Eastern Ghats belt can actually be treated as So we can actually consider the whole belt to be a combination of different kinds of geological provinces which have had distinct geological histories. Now, I'm going to be talking about this central province here. This is the largest part of the Eastern Ghats province. It's called the Eastern Ghats province, which is a part of the Eastern Ghats belt. It's granulite facies rocks, but these are mostly of Grenvillian age of 1000 MA. The metamorphism is largely around 1000 MA. And I'm going to be talking about this part which is in broad here, around the town that most of us have heard of. It's the town of Khurda. This region itself, I think many of you know, is imagined to have been once linked to East Antarctica in the supercontinent configuration we call Rodinia. Now, zooming in to the study area, this is the area of interest. This is Khurda. Now, the non-volcanic hot springs, this is Khurda town, this is the temple town of Kantillo, and this is the river Mahanadi. Now, along here, within this broad part, the red part that we can actually look at, we look at this town of Khurda. West of it is this little red spot called Atri. If you go even further west, we find this another hot spring locality, which is another village called Tarbalo. So both of these places were nondescript places of no importance till suddenly somebody who was actually making a tube well there, I would imagine for irrigation, actually found hot water coming out through the tube wells. So if you look at the trend of these two, it actually is around west-northwest, east-southeast. That's the broad trend of the line that joins Atri and Tarbalo. And if you look outside, you'll see that this is actually parallel to a major geological feature that actually controls the trend of the Mahanadi river flow. This is called the Mahanadi shear zone. It's a ductile shear zone which has existed for a very long time, and it actually forms one of the bounding margins of the Gondwana basin that actually forms this belt. And this belt itself, if you look along the shear zone, you see that it continues right through this particular region. So this is the particular region I'm going to talk about, the Mahanadi shear zone. Now, one of my students, who is Shubham Bose, who's currently an assistant professor in IIPE, he did a lot of structural and petrological work around this area and outlined the broad geological relationships of the fabrics that we see in this area. And this is what will actually lead us to the next part of what we do. to analyze why there are hot springs in an area which is seismically stable, tectonically inactive, and we have no volcanoes that we know of there, unless some is discovered miraculously within the next phase of exploration studies. It's important to develop a methodology for actually studying these hot springs. To do this, then we have to use multifaceted studies. We have to do geology. We need to do geochemistry, primarily of the waters, and we also need to do geophysical studies to actually see what's there below the earth. So the geological studies are mostly structural and petrological. We did structure, we did petrology, mineral chemistry, and metamorphism. We did geochemistry, hydrological studies. Much of this work was done in collaboration with the park, and the geophysics was in collaboration with our own department professors, and also Anand Singh, who is currently a professor at IIT Bombay. Now, the very first thing that we had to do was to look at what any geologist would do, look at the geological evolution of the study area. And the first thing we did was to map out that red-colored region that I marked out earlier. So what you see here is mostly yellow part. This yellow is quartzo-feldspathic gneiss, largely migmatitic, within which we have intrusions of charnokites, and we also find the remnants of these condolites, which are metapelite bodies, garnet sillimanite gneisses, which lie distributed throughout the terrain. Now, if you trace the penetrative foliation from south to north across the area, you'll see that there is a trend variation. So you see that there is a trend variation which appears to be curving into this broad dashed line. Now this dashed line forms the southern margin of what constitutes a major shear zones. And this shear zone is what I call a high D3 shear zone. It's an extensional shear zone that I'm going to talk very briefly about later. Both this shear zone, which actually overpins the earlier fabrics, this is cut across by an even later shear zone which trends west-northwest, east-southeast. This is the trend that's actually parallel to the Mahanadi shear zone. So we correlate this with the Mahanadi shear zone. Overlying the Mahanadi shear zone is an upper Gondwana basin called the Atkar basin. So this actually overlies a part of the shear zone and it transcends this. Atri and Tarbalo, now this is as a consequence of our mapping, we located Atri and Tarbalo, the two hot spring localities here with respect to Kurda, and you can see as per our mapping, Atri and Tarbalo actually lie to the south of the shear zone. They do not lie within the precincts of the shear zone itself. Now, if we do the petrography and the microstructure, the very first thing that I would do as a geologist here, you identify the early deformation events D1 and D2. I will not talk about these in very great detail, but what is important here is that you look at fabrics. These are very penetrative, high temperature fabrics developed at temperatures which were probably in excess of 700 degrees centigrade. And the temperatures that we have retrieved from here tell us that this early penetrative fabric formed under conditions of such high temperatures that we can classify them as constituting an ultra high metamorphic terrain. Metamorphic temperatures in excess of 900 degrees centigrade. When we move north, if you remember the map, you come across the first shear zone that cuts across this. This is close to the Mahanadi, but not essentially it. Now, this shear zone D3 is an extensional shear zone which strikes east-west. The fabrics are east-west. All the fabrics below are actually transposed parallel to an east-west trending northerly dipping fabric. These are lower temperature. These are predominantly in the amphibolite facies. But what is most important is if you do the kinematics associated with the shear zone, this is actually extensional in contrast to the compressional stresses that were associated with the D1 and D2 deformation itself. If we proceed further, we see that this shear zone is transected by the Mahanadi shear zone. The Mahanadi shear zone, if you remember, trends west, northwest, east, southeast. It cuts across the east-west shear zone. We call this the D4 deformation event, and this is at even lower temperatures. Green schist grading into the brittle regime, and you can see a variety of microstructures from low temperature brittle, low temperature ductile deformation superposed on earlier ductile fabrics to cataclastic deformation
until you get zones that are almost false. Now this cataclastic flow that you see and the angular fragmentation means that you have faults. These could very well act as conduits through which surface water can actually percolate to depths. So this is why this particular part, the D4 deformation, can be important, and this is what many people have considered to be responsible for the percolation of water to very great depths. Now, as was necessary for that study, we actually did phase equilibrium modeling. This was primarily to constrain how hot the rocks actually became. So the rocks became very hot indeed, 900 temperatures in excess of 900 degrees centigrade. Now I won't go into details to the metamorphic history, but what is important is no matter what kind of assemblages you use, the temperatures were ultra high. So this area underwent penetrative deformation, extremely high temperature metamorphism at some time in the geological past. At some time, but at what time? To do this, you have to do geochronology. Much of this was based initially on EPMA chemical ages, so these are time ages, but however, we've also got isotopic date constraints on these ages now. Broadly, you can cluster them into three groups. So you have an early event, which is around 955 to 28 MA, broadly overlapping with the D1 and D2 events. You have a later event at around 810 or so, which is not really correlatable with any kind of deformation. And then you have an extensional deformation that we can actually correlate with a 700 MA duration in the new Proterozoic. So this is something that can actually be correlated with our D3 deformation. If we try to reconstruct the whole sequence of events that this geology that this area underwent. So you started off with an area that underwent very high temperature deformation at around 955 to 28 MA. Most of the penetrative fabric was formed during shortening and crustal thickening, along with granulite facies metamorphism. After that, temperatures were actually in excess of 900 degrees centigrade. Following that, you had an event of fluid infiltration. That is probably what was correlatable with the 808 MA event that we can take thermally. And this broadly led to or preceded the extensional deformation that took place at 700 MA under amphibolite facies conditions. This was extensional, it was sinistral shearing on the surface, right? And the deformation temperatures were much lower. But then we go to even lower temperatures. When we talk about the Mahanadi shear zone, which was west, northwest, east, southeast, it's actually not shortening, not extension, it's strike slip. So we have this unique area where we get shortening, we get extension, we get strike slip, anything you want. And the strike slip deformation broadly operated, argon-argon constraints tell us, at around 515 MA. Now the Mahanadi shear zone operated as a dextral strike slip shear zone. These are all plan view features which are indisputably markers of dextral deformation. Temperatures during this shearing were much lower, around 450 degrees centigrade. The facies is much lower as well. So it's important, it's interesting, it's important to all geologists reconstructing how the earth developed. But what is important is that all this geological activity must have stopped at least 500 billion years ago. In that case, if we are calling upon hot rocks to actually do our job for us, to heat up our water, how did this water get hot? Because this was 500 billion years ago. Surely the rock can't be hot still. So there is no active volcanism, there is no tectonics, so we don't really know what actually controls heating of the water right now. So what could the heat sources be? One could be the normal geothermal gradient. So you have a deep source. So what this means is that you have some kind of fractures which allow surface water to percolate to depths where the crust is much hotter because of the natural geothermal gradient. In our study area, the D4 shear zone is probably a good one to actually talk about. This is the Mahanadi shear zone. So you also have associated small-scale local fractures which could actually allow water to percolate to depths. Alternatively, we can have anomalous sources at much shallower depths. So you could probably have things like radiogenic heat, maybe some kind of extraneous exothermic reactions. We don't know what these might be, but these are possibilities. We cannot overrule any of them. And these are important because if these are shallow, they can be important to us from the energy perspective. So it's important then for us to determine what is the actual source of heat for these non-volcanic hot springs. And how do we do that? How do we identify the source of heat? Well, the main thing we do is to look at the proxy that we get from these depths, and we need to look at the waters, because we know that in these areas, in this area, we have tube wells from which cold water and hot water come out together. They don't come out from the same tube wells, but from tube wells maybe about 20 meters apart, just about 20 meters apart. So then we did hydrological studies, both on the cold waters, which we call non-thermal waters, and the hot waters, which we will refer to as thermal waters. And this, when we do these hydrological studies, the first thing that comes across here, forgive me for condensing this, but this is a short talk, so I had to make this condense this information just to give you the summary. So this Piper diagram actually tells you that the water facies are different. So the hot water facies actually belongs to what we call the sodium chloride facies. The cold waters, the non-thermal waters, belong to a variety of facies which contain carbonates as well. We do a variety of other geochemical tests on these, and what these tell us is that the hot waters that we see, they have very distinct compositions from the cold waters. They are also more mature. That is, the hot waters have achieved much greater chemical equilibrium with the host rocks. We can actually see from this diagram also that there is a variation in the contents of the trace elements, particularly lithium, boron and lithium with respect to chloride, for example. So there is a difference here. And stable isotope studies, however, tell us that there is one similarity between the hot and cold waters. They are both meteoric waters. So ultimately, the waters we are looking at, whether hot or cold, they are derived ultimately from the surface. So the thermal and non-thermal waters are distinct in composition. The non-thermal waters are immature, that is, they're not equilibrated, whereas the thermal waters have partially equilibrated, at least with the host rocks. Now we can use these parameters to actually make source rock calculations. If they've partially equilibrated, what was the temperature of the reservoir from which the hot waters were derived? And these geothermometric calculations give us estimates of about 150 degrees centigrade, and this is remarkably consistent for all the hot waters we've seen. The low boron and lithium contents, the trace elements with respect to chloride, this actually gives us not just an estimate of the maturity, it also tells us that the thermal waters are actually older. They have to be older, otherwise they would not have been more mature. However, they're both meteoric in origin. So how do we explain two kinds of meteoric water having two different kinds of composition from tube wells which are barely 20 meters apart? Sorry. Right. So what we did is to date the waters. Now it's not so easy to date waters. One of the things we can do is a sort of qualitative dating, but that's something that can be very useful and was very useful for us. One of the things that we can do is something called tritium dating or tritium dating, no matter how you would like to pronounce it. So what tritium dating has done is that if you look at the hot and cold waters that we get, the hot waters that we have values that are well below 1. Whereas if we look at the majority of the cold waters, they have tritium contents far in excess of 1. Now, why is this important? Now, this is important because in the 1960s, on account of a large number of nuclear tests that were done by the then USSR as well as the USA, a large amount of tritium was actually released into the atmosphere. Tritium has a very short half-life. As a result of which, any waters that have actually, any meteoric water that has actually come down after 1960 has a tritium value which is above 1. So it means that if you have a tritium value of water which is above 1, this water is modern water. It's younger than 1960. And if you have values that are less than 1, it could be much older. Now, how much older? It's not easy to date the hot waters because the carbon content is extremely low. Nevertheless, Tirumalesh managed to actually...
Hello, please mute your microphone. Kaveri Rai Chaudhuri, please mute your microphone. Miss Kaveri Rai Chaudhuri, please mute your microphone. Thank you.
Okay, so the carbon dating of these hot waters actually gives us ages. And these ages, if you ask me, are remarkable. You see that ages are between 12,000 to 5,000 years. They vary. There are some which are even older than 20,000 years. And if this seems old to you, And don't be surprised, because from some Canadian gold mines and from South African gold mines, people have retrieved meteoric waters that are more than 1 billion years old. So, the continental crust can preserve old meteoric water. So, what it means is that in this particular area, although both waters are meteoric, they are chemically distinct, they are temporally distinct. Which means, of course, that even though they are coming out of tube wells in close proximity, they must be coming from separate reservoirs. There is no other way that you can get this difference. So, how do we work that out? What we based it on are surface studies. What we need to look at is what is happening at depth. So what we did was geophysical studies, mostly resistivity, and more importantly, we did very low frequency studies, VLF studies, VLF electromagnetic studies, and these were done by Professor Sharma and Anand Singh, and much of this was done by taking profiles across sections that we told them to. So what they did was to do a number of profiles across these zones that we get these hot waters, and as a result of these profiles, which they love calling P11, P10, etc., common or geophysical nomenclature for whenever they do these studies, they generated a series of images for what the subsurface was like below the hot springs at Tarbalo, as well as the hot springs at Atri, as well as the region in between them. Now, when you do this, what you see here, the blue stuff is all very, very resistive stuff. The yellow part is the part which has a lower resistivity. This means then that if you look at below the hot spring at Atri and Tarbalo, you see that there is water locked up below resistive country rock here. So this water is actually not making its way to the surface. If you actually look at the vertical depth slices that you have, you notice that the upper part is completely resistive, and you find that the low conductivity part, the part which probably hosts the hot water or the water in general, that part is actually below, it's at some depth. Look at Atri, you get exactly the same signal. Here also, if you look at the depth slices, you actually see that the low resistivity regions, the regions that actually contain water, these lie below resistive country rocks at the top. So these are locked in reservoirs. These are low resistivity zones which are actually blocked from all sides within the country rocks that you can actually see. If we look at the area between Atri and Tarbalo, this has no hot springs. You see these are profiles cutting across the east, west, northwest, east, southeast strike of the shear zones. And you see these lines here. So these all connect up. So which means that all along these west, northwest, east, southeast tending fractures, you actually have saturation of water. That is, all these fracture zones are saturated with waters, but these are all through the fracture zones which constitute the zone. What we see at Atri and Tarbalo are zones that are actually isolated as pockets, and these are very different from what you're seeing in the region in between. Let's summarize what this geophysics tells us. In the Tarbalo hot spring region, right, and also in Atri, we see a low resistivity zone. At Atri, Tarbalo, it's at a depth of 80 to 120 meters. At Atri, it's probably a little lower, and you can locate these with respect to particular profiles here. The surface, of course, has a resistive layer which prevents this water from coming to the surface. Now, this low resistivity zone, if you try to look at it in this crystalline country rock, it forms a sort of isolated aquifer. It means that water is accumulated there, and it's become entrapped, probably for a very long period. But the geophysical studies also tell us that there are geological indicators. You have these saturated water inside the fractures, but these fractures are the fractures through which water is still flowing. So we have two different types of reservoirs. We can visualize them as two different types. We have these isolated reservoirs which form water pockets. These are isolated by these resistive country rock zones. We have a second type which is flowing continually through the fractures. So this is forming a fracture network. This is continually emanating water at the surface and subsurface. If you visualize this, you can picturize it this way. So these are your isolated pockets, and this is the fracture network through which the water can actually flow through. Now, as you can imagine, if you have meteoric water percolating through, they would percolate through these fractures, but somehow they've not been able to get to these isolated pockets. These have stayed there. These are still meteoric waters, but they're still there, entrapped, isolated from these fractures completely. So then we come to this region of the heat, the source of heat for these hot spring waters. We know,
Mr. Vishnu, Mr. Vishnu, please mute. Mr. Vishnu, please mute yourself.
My apologies here. When I talk about the source of heat, now we've talked about two different types of reservoirs. But then, what could be the source of heat for the hot spring waters? Now we've seen that the hot spring waters are old, they're more mature, suggesting they've been in equilibrium with the host rock for a longer time duration. So it means then that probably the isolated pockets are the ones which are hosting the hot waters. And these are shielded from the cold groundwater that is circulating through the shear zones, simply because resistive country rock has not allowed these cold waters to percolate inside these reservoirs. How could these get hot? The most likely source of heat we can think of is radiogenic in this particular terrain. Now, what would be responsible for this radiogenic heat? Now, the most probable shallow sources of heat we can think of for these non-volcanic hot springs would be the heat-producing elements. Uranium, thorium, and potassium are the main heat-producing elements inside the crust. Now, the dominant rock types of the EGP, condolites, charnokites, QFGs, all of these are extremely rich in radiogenic elements, much more so, and it's been reported earlier in a famous EPSL paper by Senthil Kumar et al. Soil and rock samples from this area done by Vikas Baranwal in our department many years ago also tells us that these soils are extremely rich in thorium. So we know that this element thorium was probably responsible for the very high radioactivity in the area. And therefore the lithologies of the present study area, these are the plots which actually have regions that can actually contain pockets with higher amounts of thorium, probably hosted in a mineral such as monazite, which would then be hosting the thorium that we see in these rocks. And indeed, we then did the analyses of the thoriums that we can actually see. And you can see from these that the thorium contents of the monazites in these rocks are extremely, extremely high. So it doesn't matter whether they're charnokites, whether they're condolites, whether they're quartzofeldspatic gneisses, they contain monazites, and these monazites are invariably extremely thorium rich. So this was all published information, and this was all the geology. What it did tell us is that the hot water was not really heated at very great depths, but they became hot at shallow levels, and this was because they were entrapped within high heat-producing rocks for a long period of time. Now, these pockets of very high heat production, these were produced during granulite fascist metamorphism. The metamorphism occurred 1 billion to 500 million years ago. That heat no longer remains, but because of that metamorphic processing, the monazites have actually accumulated within these rocks in particular pockets, most particularly entrapped within garnets. And because they are there, any rocks that are in the vicinity of these monazite-bearing garnet-rich rocks, these have become hot with time. Now, this carried a very great message to us, and that tells us something generic which justifies our presence as geologists, that the geological evolution of a terrain, not just the present-day tectonics that our climate people begin to tell us about, this can also be responsible for the generation of hot springs at the very present day. So the heat is present day, although the reasons might have been old. So we've identified, I would like to think, the sources of the heat. We know that they are hot water isolated pockets. But now we come to the final little bit that I'm going to talk about, the geothermal energy. Can we extract this geothermal energy from these spots? Now, extracting the heat requires knowledge of some boundary conditions. What kind of knowledge do we have? We know from the geochemistry studies that the geothermal reservoirs were at a temperature of 150 degrees centigrade. What we do not know, we know that we have said they're shallow. We don't know exactly how deep it is. And if we are to extract geothermal energy, we need more precise constraints on what depths these come from. So what has been done here, this is what the petroleum engineers and Anupal actually did. So they placed these geothermal 150 degrees centigrade reservoirs at various depths, and you can bring them up in various ways. So this is a schematic representation of what might be the case. So if we are to estimate the geothermal resource in the Eastern Ghats belt, What the constraints we have are geothermometric analyses of the waters, which can tell us what the reservoir temperatures are. We know what the temperature, surface temperature of the fluid is at the surface, because the hot spring waters are around 60 degrees centigrade. What we need to calculate is something called the HIP. This is the heat in place. How much heat is stored in each of these reservoirs? Now, to do that, there are two things we can do. One is to calculate the heat, and then to constrain the depth. To calculate the heat, we will show this subsequently, and then we'll show how an engineering technique that we call Wellbore simulation studies, these can actually help us to constrain the depth and also probably suggest how we can efficiently extract heat from these things. Now, to calculate the heat in place. Now, how much heat is in place in a particular reservoir? The total heat is QT. That would be a sum of the heat that is contained inside the host rock plus the heat that is contained inside the pore fluid. Now, for each of them, if phi is the porosity of the rock, porosity of that particular reservoir, phi is totally occupied by the water. 1 minus phi is the fraction that would be the rock or the part that is not water. Each of these contains total heat, and the heat that is contributed would be a summation of the total heat contributed by both heat and the rock and water. If we look at this, we can now make guesses. If the area of the reservoir is A, surface horizontal area, and H is the thickness of the reservoir, then using this, a simple enough study, and using this reference temperature is the temperature at the surface. This is around about 60 degrees centigrade adaptary. T-res is the temperature of the reservoir. 150 degrees centigrade is our estimate. So these are the constraints we have. Phi is the porosity. So we can now have various combinations of these parameters and do something called the Monte Carlo simulation. Use different combinations of these parameters, and we did 10,000 simulations. When we do these 10,000 simulations, we try to calculate then how much would be the possible heat in place that can actually satisfy these constraints. When we do this, right, I'm not going into the details of this. When you go into this, then these P's are different from the geophysics P's, by the way. These P's tell you the percentiles. So it tells you that of all the simulations, those which fall below 10, so 10 percentiles of the simulations which satisfy these results, estimate a heat in place of about this amount. 50% would be below this amount, and about 90%, I think it's 90, would be below this amount. So these give us estimates of how much heat in place could be, depends upon the number of simulations here. Now, if we have to place some importance, statistically speaking, and this is where we have to go back to statistics, the most likely estimate is the one which is showing the model class. And this is more or less around the 50 percentile amount. And the heat in place can be estimated for any single reservoir, can be estimated to be about 1.92 into 10 to the power 13 kilojoules. So this would be the amount of heat that is present there. Now, from this, we have to recover heat. So this is the amount of heat in place. Now, if we have to recover this, this is the factor that we have to use. The heat that we can recover depends upon the heat in place. It also depends upon how efficiently we can recover that heat using our engineering techniques, right? Let's assume that our engineering techniques are 85% efficient. So we use, let's say we put in a 0.85 efficient factor here. How much can we actually recover of this particular heat? That is a recovery factor, which is distinct from CE. And of course, we have a plant loading factor. Why? Because as soon as you begin, we know that natural flow is coming out of these hot springs right now. But with time, as water, if you begin to extract water, the flow rates will decrease. So you have to sustain the flow rate. For that, you need to operate a pump, and the pump will have a load. So that plant loading factor has to be taken into account. Once you take that into account and assume that we would like this reservoir to give us heat for 10 years or so, right? Then you can use this equation to actually calculate how efficient this might actually be. So this would give us a constraint. So this gives us an estimate of the heat in place. It's still not told us how deep these reservoirs are. So that's the final bit we need to actually address. Now here we go directly into engineering, part of the engineering that I myself don't understand very well. But what we are doing here is using what is called a Wellbore simulation. So what you do is you imagine that you actually dig, plant and implant a tubing, a wellbore, which actually penetrates into the reservoir, and that constitutes of an outer cement casing. Within the cement casing, you have a part which is stainless steel, and then you have the region which is the tubing. You have an outer annulus which is separated from an inner part. Right? So if you look at a cross section through here, so this would be the host rock itself. This would be the outer cement casing. Then you have a stainless steel casing part here. You have an annular region where the fluid is able to go in on its own, and this is the part through which we will extract the water. This is the part where we will use the pumping. That is why the convection of the fluid here would be forced convection as opposed to free convection that operates in this particular space. Tf here is the temperature of the fluid. T at any particular depth. TEI here represents the temperature gradient that exists in the host rock. So the temperature gradient, as the hot water is coming up at each depth, the rock has a different temperature. At each depth there would be a temperature gradient inside the rock, and as the fluid comes up, the hot fluid, this temperature gradient will try to lose heat to the host rocks because it's colder outside. So this particular feature will continue as this hot water comes up. So this is the equation that is used to calculate this. In our equation here, alpha is really the angle at which the borehole is dug. In this case, it's 90 degrees, so this is equal to 1. So you have a number of different parameters, which also takes account of this J parameter. This is called the Joule-Thomson coefficient. What this means is that as hot water comes in through here, hot water, as you know, when it comes up will expand. When it expands, as we learned in school, it will cool. As it cools, there is a coefficient of how fast it comes up, how fast it expands, and how fast it cools. This Joule-Thomson coefficient takes place of that particular factor. So all of this, and we have this LR, which is called the relaxation parameter. It's not something I understand particularly well, but it does give us an idea of what this means. Now, when we do these studies now, these simulations now, we know the reservoir temperature is 150 degrees centigrade. So we now imagine a series of depths at which the reservoir could lie. So this is 150. So at 150, we can place the reservoir here, here, here at different depths just to see what happens. And from each of these, we use our wellbore simulation, say that if we brought up water through these wellbores, at what temperature would the water be when it reaches the surface? So if we are here, right, and we use the natural flow rates. So today at Atri and Tarbalo, there are some natural tube well outings from which this hot water comes up. The flow rates, the lowest one is 0.2 cubic meters per hour. The highest one is 4.5 cubic meters per hour. So we'll use these two extremities. So when you consider the low flow rate, if you actually imagine a depth of about 100 meters, what this means is that this straight line is the temperature of the rock. We assume a linear gradient from the surface, right, down to this particular depth, the 150 degrees centigrade at the reservoir. The fluid, as it comes up, its temperature would actually change through here to the equation I showed you earlier, so that by the time it reaches the surface, its temperature would be around 75 degrees centigrade. Now this is hotter than the actual fluid temperature we see. What do we see? The temperature is around 60 degrees centigrade. And that seems the temperature that best accounts for it would be somewhere between the depths of it's around 200 meters depth. So it would be somewhere in between here. These are the ones that would actually bring up a depth from a depth of around 200 meters, a reservoir at 150 degrees centigrade. You'd get surface water with temperatures around 60 degrees centigrade using these wellbore simulations, which is what we observe. If they were any deeper, right? So if we take them down any deeper, the temperatures when they come up to the surface would be much, much colder than what we are observing. If suppose the flow rate was higher, suppose the flow rate was 4.5 cubic meters per hour, in that case we can do the same simulations, and we can also see here. This also means that we can actually bring it up from greater depth. The reservoir could be located deeper, but there also we have constraints. It can't be deeper than 2.5 kilometers at most. Most likely within about 1 to 2 kilometers depth is the likely depth at which we would find it. Now, just for And as an example, I've kept this on. Why? This is, if I assume a gradient of 25 degrees centigrade per kilometer to be the geothermal gradient, a temperature of 150 degrees centigrade, and I'm extracting hot water from that depth through fractures, it would mean that my depth would have to be 6 kilometers. This is useless from the point of view of geothermal heat extraction. It is also impossible for heat to come up from that particular depth. I don't think it's possible. So this, I'm pointing this out because every single calculation I've seen, people use the normal geothermal gradient, extrapolate it linearly, which it is not, and try to use the depth, this to constrain the depth, which I consider to be incorrect. Now, this is the heat transfer that we see. Now, suppose we wanted to improve the efficiency and try to get out more heat from it. What we can do is to help the water to come up faster. That would retain more heat as you come up. You need to pump. So the pump efficiency factor would, of course, increase. Nevertheless, Anupal did these calculations, and what he's shown is that if we use the highest flow rate, so we just took the most optimistic case that we can think of, then if you bring it up from that particular depth, even from a depth of say 1.6 kilometers or so, you can actually bring up temperatures which would range from 80 to say 110 degrees centigrade. Hot water that can actually be used efficiently if we like. Now, all of these together mean that you can actually have different depths of reservoirs, different constraints. You can bring it up from 1.6 to 2.5 kilometers. Nevertheless, hot water can be brought up to the surface. This hot water can actually be used. Now, I'm almost near the end. So what's the take-home message that we can have? First of all, crystalline areas, hard rock areas, much of our country is hard rock. Crystalline areas invariably contain these isolated pockets of meteoric water. Now, those of you who read interesting geological literature, even remotely connected with ourselves, will read a very famous paper by the Canadian Geological Survey, Tom Gleason. Gleason actually said that in crystalline country rock, you can actually have pockets of water locked in, not hot, just pockets of water, and the volume of these waters could exceed the amount of water in the Earth's oceans by orders of magnitude. So there could be a lot of water that is actually present there. Now, this is where geology comes in. If we as geologists can identify the geological evolution of the area and identify where the HPE might be concentrated, whether there is any likelihood of the HPE being concentrated in the crust, many of these pockets may actually host thermal waters. Now, if these pockets can be identified through hot springs in the locality, in Atri, by the way, if any of you have been there, you'll see that the hot spring there is in the middle of a paddy field. Now, no paddy grows there. You can't grow paddy at 60 degrees centigrade temperature. You can't use that. So why did they actually make a tube well there? Because there was no hot water coming out of there. They made a tube well there thinking they would get cold water, and hot water started. So what they did is to puncture the reservoir. So the reservoir was already there. So what this means is that if these pockets can be identified through hot springs in the locality, their depth and geothermal potential can be estimated using these engineering Wellbore analyses. You can do this. In areas like the eastern Ghats belt, these pockets are sufficiently shallow to allow exploitation of geothermal heat. How much heat? I wanted quantities, and Anupal sent this to me last night. You can have, this is actually in our paper as well. This is from a paper, by the way, it's in a very well-known and highly rated mechanical engineering journal, right? Our topmost, including our director, has publications regularly in these. This is called Applied Thermal Engineering. What it means is that you can have about 0.6 megawatts of power. You can extract this from a single pocket in the EGB. This is enough to sustain 100 to 150 bakery shops. I like bakery stuff. You can light 600 homes in India, rural homes, which take about 1 kilowatt per home, assuming that. 10,000 street lights, 150 to 200 irrigation pumps. You can run rice mills. You can have 2 to 5 agricultural storage facilities, data service. Data service is probably the one that would be very, very useful. Now, the possibilities are you could get cases like this where you actually don't have any hot water coming up. You actually send down cold water into the earth, get it, make it hot, and pull it up, right? And then you have a heat exchanger from which you exchange the heat. This is a modification of the same thing, except that you put cold water through two pipes and then get the hot water through the central part in between. Again, have a heat exchanger, extract the heat. This is the situation we have. We puncture it, right? We puncture it here, you get hot water, use the heat exchanger, extract the heat. Now, I've ended the talk. I would nevertheless, I don't know whether I was able to properly address this. This is not an outcome of just a small project over a few years. It's an outcome of work that I've done in the Eastern Ghats over 30 years. It's an outcome of my being able to understand, right, of how this part of the clusters has been there. And even after understanding, I understand barely 5% of what there is to understand. If you look at these papers, this is Applied Thermal Engineering, Precambrian Research, Journal of Structural Geology, Geophysical Research, Journal of Geophysical Research, Solid Earth, all the ones. This is the fluoride contamination paper. The hot water is has a high fluoride content, so it's actually, we suggested some remedies for fluorosis as well. In fact, this is what gave us the money actually. Nobody else was willing to fund us otherwise. And the Mahanadi Shear Zone was done by my student Shubham Bose, who actually laid out the foundation of what we actually did there till Ashmita and Anupal took it forward. Ending this, first I would like to very much thank Shri Ashit Shah, the DJGSI, for actually giving me this opportunity to present this on such an occasion. This is something he is my college senior, and what we call in Bengali as an abdar. I told him, "Amake okhane dakho, call me here. I'll give the talk here." I could have given it from Kharagpur. Thank you, Ashitda, for calling me here. My very esteemed junior Dr. Saibal Ghosh, who has, I think, been instrumental in organizing everything that was to do with this. The training institute in charge, whom I had the good fortune to meet at Hyderabad a few days back, Dr. I think S. Ravi, Subramaniam Ravi. Sir, you're in Hyderabad. Thank you very much for enabling this. Dr. Arindam Datta, my own PhD student, who has gone through the pains of actually bringing me here. And although I don't know how much of a role he had in it, my long-standing friend from 42 years now, Mr. Shiladitya Sen Gupta, we started our PhD journey together. He did the intelligent thing, decided not to complete, and he's left me here finishing a talk in the Geological Survey of India. Thank you very much.
The forum is open for any questions. So let us take questions from the people who are there in the online platform. आप लोग एक एक mic, we will take only 2-3 questions from the online platform, please.
Good afternoon, sir. Am I audible?
Yes, I can hear you, yeah.
Good afternoon, sir. This is Dr. Nadeem Bhatt from Jammu office.
Yes, please.
Sir, I have 2-3 questions. So I want to, as sir told that we have to pose 2 or 3 questions.
I'm not sure I can answer all your questions, but
Mr. Bhatt, the most important question you ask first.
Okay, sir. Sir, for example, if there is a fluoride body underground which is causing fluoride pollution in the wells or springs, can we use the isotopes to track that fluoride body?
You don't need, what we used it for was not using the isotopes to track the fluoride body. The fluoride was actually measured. This is hydrologists or hydrogeologists can actually do that. So you'd have a particular volume at which the fluoride it can be measured directly. So the fluorides that I've talked about are fluorides that are actually measured not based on isotope, but physically measured in the field. This is a field parameter.
Yes, sir. But if we use the isotopes, we can see the recharge area. We can see the contamination using the isotope that equations. So can we use? I mean to say, can we multiply the isotopes with the fluoride to track that the origin of that?
The problem is you don't know the residence time. So you actually need to know how long the water's been down there, and when you actually find out, what age it is at the surface, exactly what would you use? Because one of the things I would again stress here, isotopes are extremely important, one of the fundamental tools we have. But they do not answer all questions. Do not expect them to answer all questions unless you actually know what you're doing. So I don't think, I can't think of using the isotopes to actually date or to time how much time they're taking to come up. So which is what the flow rate would translate into. So maybe there is, but not that one I can think of offhand really.
Okay, thank you, sir. Okay, another question, sir.
No,
Actually, we have.
Mr. Bhatt, we can go to the next person. You have given 2 questions. Let us allow others.
Okay, sir. Thank you.
Anybody else from the online platform?
Can see a number of my students, and there is somebody there.
Onuba was asking.
Hello, sir.
Onuba was asking some question.
Hello. Hello, sir.
Yes.
I am retired Professor Prakash Nasima from University of Mysore, Southern India.
Good afternoon, sir.
Okay. Good afternoon. Thing is that as your talk was really enlightening talk. So you have taken us to a different field. So what I would like to ask is whether we can use this technique in the abandoned mines. For example, say Kolar goldfields, which has gone up to a depth of 14,000 feet. So will it work out as a very good field possibility to come out with some energy through these kinds of things?
I don't know about the geothermal part, but sir, I talked about, if you remember, the 1 billion year old waters, meteoric waters that have been found in Canada and South Africa. Both of these were found from the gold mines there. So I don't know how much the heat production would be in those specific rocks, but if there are parts of the host rocks that contain sufficient heat, and if there is hot water, what I would like to stress is that you probably have reservoirs of water. Whether they are hot or not, that really would be governed by the heat production in the rock. The Eastern Ghats is known to be high in heat production. We have enormous evidence about that. I don't know about the region from the Kolar goldfield, but it is something that I would encourage you to, to advise others to do if you can't do it yourself right now. It's something that would be interesting.
Okay. Because in southern part of India, if you see, it is dissected by so many shear zones. So in all these shear zones, we find keraclasites, pseudotachelites, highly strained rocks, etc., etc. So they may give some possibility for this kind of work.
Well, yes, but as I said, a shear zone, in my area, there is a shear zone. I don't think the shear zones are responsible for heating the water.
Mm-hmm.
Next, anybody from the online
Thank you very
platform?
much, sir.
Ramesh, Mr. Ramesh.
Sir, good afternoon, sir. Thank you so much. It is a very enlightening session. Am I audible, sir?
Yes, you are.
Yes.
Yes, sir. Yes, sir. I am having 2 questions, sir. One is there any estimation made by any institution or IIT Kharagpur or even GSI that what is the actual geothermal potential in India?
Well, there are 2 parts to this question. IIT Kharagpur part, Mr. Satla, you yourself can answer because you're registered there as a PhD student, so I sign your forms.
Yes.
So you can do that. For the Geological Survey of India, I am sitting with all the stalwarts here. Not a question that I can answer, I think. Well, nobody can answer as far as I'm told here. We can discuss this when you come to Kharagpur.
Yes, sir. Sir, one point I would like to bring through this conference to the GSI, that, sir, there is one figure mentioned in the GSI Geothermal Atlas of India 2022 published, wherein it is mentioned 10,600 megawatt geothermal potential exists considering 113 geothermal sites out of 340 hot springs located in India. But this figure is misleading many policymakers and even the scholars, that though actually the geothermal potential is very high, this figure is being carried out by MNRE publications, by many PIB publications, that 10,600 megawatt is the potential of the Indian subcontinent. So this figure needs to be relooked, sir, and according to the preliminary estimations we have made, it should be in the order of at least 500 gigawatt if we consider the EGS and the conventional geothermal systems. So I request the GSA authorities to kindly look into this figure.
Okay, we will look into that. Definitely we will look into that. Thank you for your good suggestion. Anybody else?
Thank you, sir.
Last question from the online platform. Last question.
SUAP.
No.
Any other questions? Open the chat box here.
Dr. Sajeev, no. I mean, is my answer to your question.
You can see the question and answer.
Can I see the questions? Yeah, okay.
Orindam De.
Orindam there, sir, as you talked about the geothermal heat from the Indian shield, where the heat may be pockets in the reservoir, tectonically active zones, northwestern mountain belt, or what are the possibilities of the heat other than intrusive rocks which contains radiogenic elements? Well, for example, I think Puga is a very well-known place, right? I mean, so there is where I think ONGC is actually doing some kind of geothermal. And GSI. Okay, my apologies. So, so there are plans afoot actually to do this. The north, I see, tectonically active regions are always regions where there is a greater geothermal potential. Especially hot rocks have been advected to the surface, so that you can have elevated geotherms in many places. So it is definitely possible. I don't know what you mean by intrusive rocks. I mean, the intrusive rocks, it depends on how old the intrusions are. I mean, if the intrusions are billion years old, of what use is it that the rock was intrusive? If it contains radiogenic elements, that's here. But for granites, for example, granites are very high in heat production normally, but not all granites are necessarily high in heat production. Now, this is another aspect, I mean, which this gives me the opportunity to stress that, heat production studies, I mean, apart from the lab in the National Geophysical Research Institute, and I think one in Punjab University, I don't know if there are many other places doing this. So you need much greater estimates of radiogenic heat production. So maybe with Dr. Shukanto Rai and with Dr. Labuni Rai at NGRI, Shukanto Rai at BGRL, I mean, these are things that can be discussed. These are facilities that should be developed. We have a gross shortage of people who are working in these domains.
Okay. Thank you. I think both are already answered, sir. Already done. Sajeev is also done. Yes. Okay.
Anybody from here?
Anybody from this audience? Any question? Sudeep, please.
An excellent look of this. Only question. Just one thing. So up to this 120, 150 or 200 meter depth, as it is in the sealed area. So the GSHP can be used to extract the heat source from here, ground source heat pump or like that, because normally ground source heat pump is being used for the low enthalpy zones. So for the high enthalpy zones like this, can it be used up to that depth or not?
GSHP means?
Ground source heat pump, that is normally being used for the freezing or cooling or heating of this. In Iceland and everywhere.
See, the thing is that again, in active geothermal areas, right? I mean, these are established technologies. The technology we are talking about is something that we have to develop for low enthalpy areas, because much of our country, and if you're going to use it in, say, somewhere in West Bengal, for example, right, or Purulia, here, I mean, we don't have these alternative sources of heat. So you have to develop technology which is cost efficient as well as, can be beneficial. Now, I don't know enough about GSHP to be able to say this, But I mean, the technology part is the part that's why, I mean, my job really was to create the bridge between the engineers and the sciences that we do. So they know what's there. Now they can actually tell us what is possible and what is not. So, I mean, the technology part of it, Shudip, I'm afraid, I mean, I don't really know.
Just one information that has been told here, that is the Geothermal Atlas 2022, the figure given here. It is obviously it is not actual now, because we, for the entire country now, I also attended this MNRE meeting there. So there it has been told that according to the UNFC rule, what are the, it has been done in Geneva 2023 there. So according to that policy framework, UNFC, so different stages are there, G4 to G1, and within the G4 base there is also subdivisions, G4.1, 2 and 3, so all this. So these are there, so accordingly the resource calculation now we are introducing in the Atri, Tarabalo and our this Ladakh also. So this has been taken care of. So but the preliminary one, it was just like that, or the quartz thermometry or different thermometry, what is the reservoir depth, no geophysical thing was there like EM, MT like that. So you have to go to the particular depth according to the resistivity of the rocks, as you have told. So this is very important, and we are in the process.
Now, one thing I'd like to say, you're absolutely right, but I would also think that our estimates that we publish should be conservative.
Yeah.
And when it improves, I think that's much better. The second thing my learning from here was, geophysics I thought was telling me, you see, geophysics tells us where the water pockets are.
Yeah.
They don't tell me where the hot water pockets are.
Yeah.
So that is where the Wellbore simulation part, I mean, at some stage we have to fall back on theory. And that is where, unless we do transdisciplinary work, it's not going to happen. At the same time, if I did not measure dips and strikes in the field and look at thin sections, this would not have been possible.
Sure. So thank you, sir.
Sir, one is that it is a non-renewable source, the one which you have shown. It's not renewable, no? So it does not count MNRE.
It's
But hot water is gone forever. No, isn't it?
yes, but you can always heat up geothermal energy.
No.
Energy is
the pockets. You will not be
the
able to
pockets,
heat it
yes,
to 12
absolutely.
And then your the diagram which you showed, the one through geophysics which identified the pocket is about 150 meters or so. Then why are you using 1.6 kilometer for modeling it?
Because very valid question. You see, again, the question is what I told Shudip. We published it. I mean, this is where you play tricks. We published it saying that this is just above the pump where the hot water is, not the pump, the pipe where the tube well where the hot water is coming up. So we get this 160 meter depth thing. We know that there is water there from geophysics. We don't know that it's hot water. So
But
that is
the
the
one
thing.
who have drilled the water, who got the hot water, they must have known the depth.
No. They didn't drill it for hot water. It's in the middle of a
got the
paddy
hot
field.
water, no?
They got it. And the thing is that it's not exactly identical. If you actually look a little closely, they're laterally displaced. And in Atri, for example, I don't know how many of you have been to Atri. In Atri, as soon as they found the hot water, they made it a temple and you can throw coins,
How
etc.
deep was that well?
It's not very deep, and in fact, inside the well, you can see a pipe through which bubbles are coming out. So, what natural God would have made a pipe, to bring up the hot water? So, it was done because somebody tried to dig a well, and hot water started coming out, and they tried to. I think it's become a temple business now. But the thing is, barely 20 meters away from that, just outside that compound, there is a cold water pump, and that is just less than 50 years old. That water.
You can use gravity finding the pockets, water pockets.
Again, you can identify gravity, yes, but gravity works better on large pockets because the values are so small.
So how do you? What is the method you do? If you do
Resistivity. Resistivity and wear.
Countrywide.
Countrywide, you'll have to use a combination, right? You'll have to use a combination. I mean, I think what I've learned is that you need to use several methods in conjunction,
It's a
and
long-
it might be case specific.
It's a long project.
If the geophysics can't recognize the hot ones,
Hot water, I'm coming to that. If you do magnetics, If hot will demagnetize the body, then you can know a demagnetized zone that can be a hot water source.
Probably it depends upon the extent, what is the magnetization or the magnetic susceptibility of the host rocks themselves, how magnetic are they, and whether the difference is measurable.
It will be, they will have differential.
There will be a difference, whether it's a measurable difference or nanotesla. Is the
Sandeep, if you have a question.
Sir, one small query. Sir, in your Monte Carlo simulation, you shown that there is a depth based and flow based modeling. And should we consider there the rheology of the rock, means porosity and all this, because the water flow depends on the, if it is a granite, it will be different.
For the heat in place, you don't need to do that. I mean, it is being automatically taken care of when you're taking the density, specific heat capacity. That way the rock type is taken care of. It is simply estimating how much water is there, how much heat is there, sorry. Right? So the rock type part comes in much later. I mean, we need the physical parameters for the rock much more than anything else. There may be the engineering geology measurements of the rock properties probably be more useful,
And
I would
in
think.
the thrust belt, whenever you see the Dirang MCT there are a lot of hot spots and these hot water springs. In the thrust belt, this model will not, there is a different modeling or something.
Because these ones, I mean, you see, those are also interesting because I'm still, you see, if you think of a rock coming in, hot water coming in from, say, 5 kilometers, how fast must it come? It's Darcy flow, it has to be Darcy flow. If it's coming up through Darcy flow, through that, how does it retain that velocity? So there must be a huge pressure head. And this I find very difficult. Here it's coming up from a shallow depth simply because of the thermosiphoning effect. Because you've got a lot of water, the cold water would go down, the hot water would come up, so that is responsible for the flow rate. That's how we identify. Otherwise it would not have come up at all. The principles we use in tectonically active or volcanically active places would be very different from what we are using here. The technology has to be different.
In tectonically active, how deep does the water go? It's basically metallic water again going down, getting heated up, coming up.
Yeah, I mean, I did some papers, for example, in the Rockies. It goes down a lot actually, but the recharge is right at the top. But when it comes up, you actually get the hot spring at the foothills. So actually, you have a pressure head.
Say in Chumatam or Puga, you actually get in a valley.
Yes, but Puga, I believe they believe there's some kind of magmatic reservoir there, I think. I'm not very sure. I mean, I've seen a lot of published stuff, but I would like to apply this and see.
Parashar is not.
But even these pits are possible even if there is no shear zone as such.
The thing is to get the water. See, one of the ideas, again, the structural geology idea, again, nature papers, is that, say, the Indian crust or any part of the continental crust is always in a state of critical stress. Because of the plate movements, the crust is always in a state of critical stress. What that means is that ariktu dhakka dili, it will fracture. So fractures are always there. Now when water comes in, water will go down. Right? As long as there is air, water will go down. Water will displace the air, water will percolate down. The question is how deep can it go down? Once it goes down, then it seals off. So that fracture might close. So that is how you are entrapping the water.
Okay, তুই একটুখানি
ধরুন অনেকগুলো করলে, but depends on how explain.
স্যারকে কিছু বলতে বল।
See, Google and Microsoft, why should they do it? That means, there is something that they found.
But they are doing in Kenya, the fractures. That is different purpose.
That is true. I have not told all of them because they use it mostly for data center cooling. For server cooling, it's a major source.
We can help in identifying the pockets, but with national program, but as he says, kind of small sizes, just gravity will not do, we must go to different depths.
One of the first things is to identify these small pockets. That can be done.
Geophysics.
So I believe there are
I don't believe.
no.
Oceans, I don't believe that.
That's Gleason's idea. I don't know.
Oceans are there, I don't believe that.
not oceans. They said that the volume of water. Don't listen, yeah. I mean, I met him actually. He came to Kharagpur.
If you see the mass of the earth, whole mass of the earth, and the porosity of water is still sufficient. If you see the whole mass, and then you consider the complete solid mass, solid or liquid, and the porosity also.
No, but if you read the nature paper, it's not unconvincing, you know.
They have given calculation. See it in the 3D. Don't think only about the oceans and the depth of the ocean. If you see it in the whole earth, then that thickness of the ocean is nothing. The crust is always crustal.
See the estimates say ringwoodite. Ringwoodite is nominally anhydrous, so it does not contain water theoretically. But they are estimating there is more water there than
Ringwoodite
so.
they are using to shade the full of water. That is the difference.
Okay, sir, thank you so much. Thank you so much for accepting my invitation and be there and giving a vibrant lecture. So I've seen that you are 20 years back, the same energy you have, still you are pursuing that one in the class, in the field also. Thank you, sir. Now I'd like to request our Director General, sir, Sri Ashish Shah, sir, so for our closing remarks, sir.
Okay, I just want to say that we are fortunate enough to have Dr. Saibal Gupta here, even though he has been very modest in saying that he has asked for this event, but it's not right in that manner. We actually have have thought of an event which will go on not only for this year, but for the times to come, where we would request all the stalwarts who are there at this moment in this geoscience domain all over the country to come and deliver lectures on the topic of his or her choice for the broad geoscientific community. And today we have started this journey, this webinar series, as part of our 175th year celebration. We started this with Saibal. I'm just thankful that he has accepted this invitation, and our plan is to have one such webinar every month, because we would have loved to have more frequently, but that is absolutely not possible because of logistic reasons. But once a month, yes, that is possible, and we are going to do that. And I would like all the participants today who have been aptly listening to this great deliberations to wait eagerly for the next one. We promise that it would be equally interesting and thought-provoking. So thank you for joining this. Thank you everyone who has joined from GSI and also from outside GSI. We would like to have more participation because this is purely for knowledge sharing and provoking thoughts, innovative ideas. Our young scientists who are there everywhere within GSI, outside GSI, we would like them to listen to this lecture series and get new ideas, new motivation to take this geoscientific journey forward in this country. Thank you very much.
Just information. One information to all. This has been done through YouTube Live also, and it will be kept also YouTube link. So please share this with others who are interested on geothermal energy.
Okay, sir, thank you, sir. So just a minute, sir. So now I would like to request our Director General, sir, to present the memento to our distinguished speaker. Now I request our ADGPSS, Dr. Joyce Bhakti, sir, to present this to. Sir. Okay. Thank you all for joining. Thank you.
না না খুব সুন্দর মানে ready to see. What ready to see.